Thank you to the organizers for such a wonderful meeting. The week has gone by quickly, and I can't believe it's already here, the last day, but thank you so much for organizing this. And so I will talk today about volcanoes, and from my title you can see I put the elements here: earth, I'll talk about seismic, wind, that's infrasound, and fire, we're going to let that be the lava that comes out of the volcanoes. And then I thought, since there's four elements, I'll also say one slide about water, because you have to have all four of them. And this is showing Great Sitkin volcano in the Aleutian Islands. This is effusive eruption of a lava dome at the summit of the volcano. And we'll talk about Great Sitkin today. Here is a list of the collaborators who helped me with this research. Okay, so just to give a brief background on where I come from, Alaska. So this is a very active volcanic area in the world. 54 historically active volcanoes in Alaska. We only have instruments on as many as 35 of them, so many of them are uninstrumented due to logistics of working in this very remote region. We have 1 to 3 eruptions per year on average. Right now we have 2 volcanoes at elevated color code, orange and yellow, Great Sitkin and Shishaldin. Great Sitkin is today having continuing effusive eruption of that lava dome at its summit. And our most important hazard are the effects of ash on aviation. Here you can see the North Pacific air routes. It's a sparsely populated region in the Aleutian Islands, but over 50,000 people per day fly over them. And we want to keep the plane's jet engine safe. Also, you can see here from the eruption last year at Shishaldin, ashfall fell at the airport in Cold Bay, Alaska, and closed it for a week. So how do we do that? We have this network of geophysical instruments in Alaska Peninsula into the Aleutian Islands. It stretches over 3,000 kilometers. It goes into the eastern hemisphere. Those are the furthest volcanoes in the Aleutians. And this is showing that over the past decade, our network underwent a major upgrade from old analog equipment to digital. So now it is a fully digital network. These are just showing some of the sub-networks, seismic stations, but in there we also have infrasound. So here I'm showing single station infrasound and also arrays. The arrays are shown here in red. Those are the locations of the arrays. Here's just some pictures of how these arrays are set up, and I've been inspired this week by the posters and presentations on optimal array design. So I need to go back to Alaska and discuss how we can optimize these arrays. Here's 2 looks, and then also single station. You can see here in the bottom panel of this recent paper by Wes Thielen that here now in 2022 and even more now, there's a regional infrasound network. It's not even shown in 2010. It didn't even exist. So infrasound has really built out over the past decade in Alaska. And of course, we have webcams too at our stations, remote cameras, and we catch these animals that everybody knows in Alaska. Here's a bear on the first Aleutian island chewing up a GPS cable. Here's a bear destroying a seismic station. That's what it looks like. So yeah, we have these webcams too. Okay, so just an overview of the talk. I'll start with some background and examples of volcanic infrasound, and then I'll give 2 case studies. The first one is infrasound, or acoustics, atmospheric gravity waves produced during the eruption of Shishaldin volcano during its eruption last year. And then we'll go to Great Sitkin, where we'll look at Coda wave interferometry, so a seismic case study there at the end. Okay, so infrasound. Many of you are probably involved with infrasound, but I just thought I'd review it. What is it? When I first came to Alaska, I did not work with infrasound data. So it's sound below the threshold of human hearing. Here you can see in this plot, infrasound goes up into the atmosphere, seismic down into the earth. I've seen volcanoes explode like at Kilauea and not make a sound that I could hear. Some people I've talked to that work at active volcanoes say you can't hear infrasound, but sometimes you can feel it hit you in the chest. So that's infrasound. We're looking at low frequency sound. And then here is profile of temperature in the atmosphere. Sound speed scales with the square root of temperature, so this is also like the sound speed. So you can see the atmosphere has layers just like the Earth, like crust, mantle, core, except troposphere, stratosphere, mesosphere, thermosphere. And a difference with seismic is near the surface of the Earth, it decreases in velocity. That's in contrast to the Earth, which is usually increasing in velocity with depth from the surface. Okay, so infrasound now. Sometimes people also say seismoacoustic, so here's a simple slide showing an explanation. This is showing that, seismic and acoustic in the atmosphere are coupled. Traditionally, we treat them as uncoupled, like from the seismic point of view, a free surface, or from the infrasound point of view, a fixed surface. But in the Earth, we can have, this is for normal incident P waves coming down. They can convert into air-to-ground coupled waves, or the reverse. Coming up from the Earth, we can do ground-to-air coupling. So that's another interesting aspect of infrasound, is to look at its coupling with seismic. Okay, and here in this slide, I just wanted to make an analogy with between earthquakes and volcanoes. They're very different phenomena. They don't, they're not the same, but they have very similar sort of measurable properties. So here on the left, I will show a fault, tectonic ruptures, and then volcanic eruptions. So I'm not an earthquake seismologist, but I understand, the area of the fault is important, the slip velocity, the stress drop. These are typical quantities discussed for large earthquakes. At volcanoes, we have similar physical parameters. Instead of area of the fault, we talk area of the vent. Instead of slip, exit velocity of the material shooting up out of the volcano. And then instead of stress drop, pressure drop inside of the volcano. And then I also here highlight a difference with volcanoes and large earthquakes. Is in volcanoes there are well-established precursors that are monitored. So before we get to this point, hopefully there are micro earthquakes, gas emissions, deformation of the volcano due to the intrusion of magma. There can also be heating of the surface of the Earth that can lead to, in Alaska, it can melt glaciers that are on top of the volcano. So in acoustics at volcanoes, this is from Sylvie Vergniaud, a paper from 2004. Volcano infrasound researchers often discuss, what is the nature of the acoustic radiation? Is it monopole, dipole, quadrupole radiation? So this is commonly discussed in volcano infrasound. So here, for example, dipole. This is modeled as a force at the vent of the volcano. And so I was just going to highlight this. I worked a few years ago on a paper where we explored, what is the analogy of this sort of monopole, dipole, quadrupole. So this is looking at the dipole, and we wanted to look at what does that mean in seismic. In seismic, we talk about forces and moments. So here is shown an acoustic force source, or a dipole. It's a pair of an explosion and implosion. You bring them close together, and in the limit, it's the same as acoustic force. So that's what they infrasound researchers talk about a dipole. So what does that mean in seismology? We looked and we came to this conclusion that, and you can show this mathematically, that in seismic, because we have P waves, we have also a explosion dipole, but then perpendicular to the force, we have a torque dipole. And when you combine that torque dipole with the explosion dipole for the Earth in a very precise ratio between the two dipoles, you can recover perfectly the same radiation as a seismic force. So it's, this is showing, with our forces, we are looking at the dipole case that oftentimes infrasound researchers are talking about. So moments are quadrupoles, and then these are our monopoles, explosion and a torque source. A torque source, here's in 2D, it's just a twisting of the cylinder. Okay, so that's some of the concepts. Then I wanted to just show a few slides about kind of the nitty-gritty of monitoring that we do at AVO. So we've seen a lot of beamforming shown here at the meeting. We also use this in our routine monitoring. So we hardly ever look at just raw infrasound data. We want to process the array. So here's shown for one of the arrays in the Aleutians. A subpanel, this is what we often look at. We do a procedure called least squares beamforming, where we look at the waveform. This is the similarity. We highlight here the trace velocity across the array. So here we have a window of interest around 300 meters per second. And then from this processing, we can also compute the back azimuth from the array to the source. This is actually an eruption for Boguslav volcano north of Akhmak. So yeah, we use this processing for our web displays and also for our real-time alarms. Okay, so this is the part about water that I wanted to show. So we show all 4 elements. And for this, we're going to take a trip from Alaska Aleutian Islands to actually another part, a volcanic chain that we monitor, which is in Northern Mariana Islands. It's part of U.S. territory, the same as Puerto Rico. And in addition to Alaska, we also monitor Northern Mariana Islands. So here I will show, this was an eruption last year in September at Ruby Volcano. This is one of the main island of the Northern Mariana Islands, Saipan. So 50 kilometers north-northwest is a submarine volcano called Ruby. We have seismometers and infrasound sensors here on Saipan, but we also use CTBTO hydrophone arrays at Wake Island. These are over 2,000 kilometers away from the Northern Mariana Islands, and it takes about 25 minutes to propagate when you have a submarine eruption. So we monitor these hydrophones as well. And we collaborate closely with Olivier Hivernode at Tahiti on these detections. So here's last year, we detected this eruption. It started in September, and so here you can see on the local seismometer, here is a eruptive tremor in spectrogram. This has happened, it ends at 4:50 UTC, and then 25 minutes later at 5:15 on the hydrophones, we see the same. So this is another aspect of infrasound and hydrophonic signals, is they propagate very long without distortion of the or attenuation of the signal. So this is the same as our infrasound setup, except now we're looking at 1.5 kilometers per second, the speed in water. Okay, and here are a couple examples of research with infrasound, and then I'll get into the case studies. This is papers I published a few years ago from the Boguslav eruption in Alaska, and this is looking at low, middle, higher infrasound frequencies, 1 to 2, 2 to 4, 4 to 8. And then this is lightning data. So there are global networks of electromagnetic sensors that detect lightning all over the world. And so this is showing an eruption of Boguslav. And what we're seeing here in the low frequency is this is 1 to 2 hertz. That's the material coming out of the volcano. So you can see it erupts, it takes a break, and then it erupts some more. So that lower infrasound is proportional to the eruption. Here in this middle part, we started to see these additional signals here that are moving. This is at back azimuth. They're moving to the west after the eruption is done. And then here also is even higher frequencies. It has this pattern. And so what it's showing is this is the eruption of mass out of the vent, but here in these higher frequencies, we are detecting thunder from the drifting volcanic ash cloud. So when it stops erupting, the ash cloud drifts to the west, and inside of the ash cloud is this phenomenon of volcanic lightning, and we can track that with this infrasound array. So this is additional ways of observing this electrification of ash plumes, and we use volcanic lightning in our alarms at Alaska. And then here's the second one I was going to show. This is kind of similar to the work that Celine showed with determining back azimuth from rotational sensors. It's different, but it's in the same spirit. We have here a classical infrasound array. This is our preference to have that. We've done some work on nearly co-located seismic and infrasound. This was published a few years ago. The acronym is GCABAD, which if you're a guitar player like me, this is a really cool alternative tuning of a guitar. You should try. But then there's also this work co-located infrasound and seismometer. So perfectly co-located, can we get the back azimuth? And we looking at minimizing the transverse coherence between the two signals. And so this was published last year by Jordan Bishop, who's now at Los Alamos. And this is just showing for this eruption of Great Sitka, we had a station to the west, and here's the signal. It's coupling between the seismometer and the infrasound. There's coherence. There's two possible directions that come out from coherence, but if we look at retrograde, which one is retrograde elliptical, then we pick out the correct back azimuth to the source. And similarly to the east, from the retrograde assumption, we can discern between these two. So from a single co-located infrasound seismometer, under this retrograde assumption for the coupled wave, we can see the back azimuth without an array. Yes? It's a type of surface wave between a fluid and a solid that has, for a homogeneous half-space, homogeneous fluid, it's a retrograde. But we're continuing this research. There turns out it can go prograde, so continuing to look at those conditions. Oh, for this? For what? So it's shown in this paper, and we look at the coherence. So we scan over possible back azimuths, and you get a peak when you're looking at the radial direction, but the peak is very smoothed out. And so the trick is by looking into the transverse, the valley is very sharp. So you can get the transverse direction, which gives you two transverse. So then you know the radial, and then you can look at the coherence of these two co-located ones, and you can pick this out. Yes. Just we don't look at we use the vertical one for the coherence measurement, but not for the direction. That was from the horizontals. Good question. All right, so now the two case studies we'll look at, Shishaldin and Great Sitka. We'll start with Shishaldin. It had eruptions last year, fairly large ones. It's the largest eruption at Shishaldin since at least 1999, and it's probably even larger than that one. And what I'll show here are observations of very low frequency acoustic gravity waves. And I'll talk about a model and apply it to one of the 13 explosive events. Okay, so this is Shishaldin volcano, and then this is one of the closest communities, Cold Bay, Alaska. And I'll show some data from Cold Bay, some meteorological data. And so here is the motivation for this. This is what we noticed in near real time. For the 11th eruption of the sequence on September 25th, we looked at these two stations here, SSLN, SSLS. They're both about 6 kilometers from the volcano. And here's the raw seismic data. This is the buildup, and then this is the beginning of the large explosion that happened. And then here, co-located, are for SSLN and SSLS the infrasound, except we've bandpassed it between very low frequencies, 300 to 1,000 seconds period. So we see this very low frequency signal here. And it's since they're basically the same distance from the volcano, it arrives at almost the same time. Then for this other station, ISNN, it's further away. We don't have an infrasound there. We should and we will someday. But we do have a seismic, and by doing the bandpass on the same frequency, 300 to 1,000 seconds, we see a similar signal. So this is coupling into the seismometer. But look at this, 18 minutes. That's, given the distances, 10 meters per second. So this is much slower than infrasound. So this is already indicating to us that there is some acoustic gravity phenomena. It's a very complex type of wave propagation. So acoustic gravity waves, these were studied in a seminal paper by Kanamori and others in the 90s. And there's 3 frequencies that govern these. One is the acoustic cutoff frequency, what's called the Brunt-Weissalo, I'll call it BV frequency, which is here in this plot by Kanamori, and then I'm going to call it geometric frequency, which is this even lower peak in the spectra. And so, yeah, that geometric frequency is always less than the Brunt-Weissele frequency. This is the oscillation frequency due to the layering of the atmosphere. The atmosphere density goes down exponentially with altitude. So typically they plot this type of phenomena in a plot like this, where here's the Brunt-Weissele frequency. So all infrasound exists above the acoustic cutoff, which is a little bit above that. And then below that are these gravity waves. The only wave that passes through that boundary is the Lamb wave, which was the wave that was excited by the Tonga eruption and propagated around the Earth. But I don't look at that here. I'm looking at these internal gravity waves. Okay, so these are very strange waves. Here's a plot from a book by Lighthill. So the phase and the group velocities directions are perpendicular to each other. So if you were to throw a rock into a pool and excite this type of wave, it wouldn't be circles that came out. It looked like the sun. It would come out like this. So here's an indication of what it looks like. Very slow propagation velocities, and it's been discussed previously at Montserrat in the Caribbean, where Repepe and others saw these low-frequency types of waves from large explosions in 2008. And they all are only observable very close to the source. Okay, so here's a summary of what they found at Montserrat. They did a stacking analysis and saw the transition for these signals at Montserrat from 10 meters per second up to, as the increased frequency, to what we expect, 330 meters per second. And when they did inversion, they found a source elevation at 2.3 kilometers above the vent, which they interpreted as the upper limit of this lower momentum-driven part of the plume. They call it gas thrust, before it became thermally buoyant. And they found a total erupted mass from these waves, and it agreed well with the field geology of the mass erupted from the eruption. Okay, so we're going to apply this at Shishaldin. And to do that, we use similarly this paper by Kanamori. This is, I think, the only equations I'll show in this talk, but Kanamori derived, the step response for a mass source shown in this equation. Here's some details, but this assumes a homogeneous isothermal atmosphere. You integrate these numerically, and so it's the step response. So you take the convolution with the time derivative of the mass eruption rate to get the response to a particular eruption. Okay, so we apply this at Shishaldin for event 11. Here's a plot of high-passed infrasound from that eruption. So here, the tremor increased for 2 days before. Here's this increasing time period when it's sort of just having small explosions. And then it went into what is commonly called a paroxysm. So that's just a sustained half-hour, hour-long period of elevated eruption. And it shot a ash plume to 14 kilometers. Volcanic lightning is detected in that ash plume. So here's a zoom in on this transition from repetitive explosions in the infrasound, you can see, and then it just goes right into the paroxysm. Okay, so that was a high-passed version of the infrasound, but here I'm going to do instrument correction over a very wide frequency band. And so here I'm going to very low frequencies, and now you can see at that time of that transition, in the infrasound sensors that we put out, we measure very low frequencies. These are the ones we saw in the bandpass data earlier, except now it's instrument corrected. And so you can see we have frequencies at, here in the frequency spectra, at 11 and 22 minutes. So these are very long period oscillations of the atmosphere. And here, quickly we can identify the Brunt-Weissele frequency at 1.5 millihertz. And we can check that using radiosonde in the nearby community of Cold Bay. This is our radiosonde data in the atmosphere, and from the potential temperature measurement, we can measure the Brunt-Weissele frequency, and at the surface, around this time of this eruption, similarly about 1.5 millihertz. So that is the Brunt-Weissele frequency. This is also the temperature profile. Okay, so now with that information, we do an inversion for the mass eruption rate. Here's people have used different source time functions. Here's some that Kanamori used. Here's one that was used in the paper by Ripepe. These are fairly impulsive. Here at Shishaldin, we use a time-shifted Gaussian function, which is more symmetric. And so we scan over, sorry, I forgot to say it. We scan over this duration parameter, tau, here, and also the elevation above the vent. And we find the best match of the synthetic and the data for time duration of parameter of 170 seconds and a source elevation of 4,500 meters above sea level. And so here's what the waveform. It didn't fit it as well. No, I don't think so. The step response. So then this is the fit from this. This is like a Gaussian type of fit. So it's trying to fit the waveform itself. This is what we found. We tried a few different source time wavelets, but this is the best fit. You can see here the mass eruption rate in kilograms per second. Here's the fit. It's pretty good here at the beginning. Less good here at this second part, and I can speculate on why that is. But when you integrate the mass eruption rate, you get a total mass, which agrees very well with independent measurements from sulfur dioxide using a totally different methodology with satellite measurements of sulfur dioxide. Okay, so we get this mass eruption rate. This is one of the very important parameters of volcanology. It's a factor of 2 larger than what they found at Montserrat. This may come to your question, Nicolai. The source time function was symmetric at Shishaldin in contrast to the more impulsive ones at Montserrat. And this may be due to Shishaldin being an open volcano. There's no cork or mound of lava dome at top. So it's open. Perhaps that explains the more symmetric source time function. Here I'll skip this. So it's a very similar elevation that we find above the summit at Shishaldin compared to Montserrat, 1.7, 2.3. So this is the upper limit of the gas thrust region. And then finally, we'll look in the future at other eruptions. This was just event 11. But from that very low frequency infrasound data, we can get the mass eruption rate, which is a very key parameter, similar to seismic moment for earthquakes. Okay, so then this last part, this is looking at Great Sitkin. So this is going to look at ambient noise Koda wave interferometry. And we've seen a lot of very cool presentations on Koda wave measurements. So I think here I can go a little faster. We're familiar with this method. This is looking at seismic data. And Great Sitkin had an explosive eruption in 2021 that is continuing now as an effusive eruption. So here's our subnetwork at Great Sitkin. There's 5 stations on the edifice. This one was not working in real time, GSTD. It's since been filled in. They pulled the card on it, but I haven't had time to process it yet. So I look at these 4 stations. And then at Great Sitkin, this is just a time depth plot of the seismicity. Over the past many years, it's been in unrest. It's been having many volcanic earthquakes, some down to 30 kilometers depth. Some the size of this one in 2020 was 3.5, so a lot of unrest at Great Sitkin. But then, interestingly, if you plot here the volcanic events, there was a phreatic eruption in 2018. You can see it there. That's a steam-driven eruption. And then in May, an explosive volcanic eruption that was captured amazingly by Fish and Wildlife Service. This is an incredible photo. It's usually not this weather in the Aleutian Islands, and they happened to be there and snapped it perfectly. And then after that explosive eruption, then it went into a quiet period of effusion. Not a lot of tremor, not a lot of low-frequency events. And so that's really good for Koda wave ambient noise interferometry. Not a lot of interfering seismic signals with the ocean noise. Okay, so this plot, I don't think I need to go into detail. We're going to use on the ambient noise correlations. These Coda wave interferometry, here are some of the parameters. We look at 0.5 to 2 hertz, and here are some more details. But we look at both positive and negative lags. So when we do that, here it is over 3 years. So the positive lag is in blue and the negative in black. So we want to make sure they give the same. Otherwise, it's not high confidence. So it's, having some, at these two station pairs, not a lot of change. And then here's August 1st. Both of these pairs, we see an increase in the dV over V. It's getting to for these, it's, apparently 0.5 to 1% change. So it's an increase. This is similar to what Zongwen showed yesterday at Iceland, an increase when the eruption is happening. And a similar increase was reported by Wegler and others at Merapi. The opposite effect was seen at Montserrat by Bapti when the dome was destroyed, then the velocity decreased. So here we'll go look in more detail. We have 10 total correlations. We have 6 cross correlations and 4 autocorrelations between these 4 seismic stations. And we're just looking at vertical component. So what about August 1st, 2021? Why is that significant? Well, there was the explosive eruption in May, and then on August 1st, thereabout, this is from remote sensing, looking at high-resolution satellite data, the dome began to be extruded at the summit of the volcano. So here, every time there's a good satellite image that's clear, they are measuring the dome volume. So here I've just cross-plotted here this particular station pair, and you can see a remarkable agreement between this sharp increase and continuing increase in the dome of the volcano. So the increase is directly related to the effusion of lava at the volcano, and this is this is the most significant effect. There could be other effects here. I'm not going to interpret them right now, but this is the first order change that we saw. And so, this is the data outage. It was later filled in. Then our next analysis is we looked at the work of Ann Obermann, looking at the radiative transfer kernels, and we coded it up according to the 2013 paper. And then we look at those 10 either auto or cross correlations and map it out in space. So here's the result. This is the percent velocity change. And at those 4 stations, the 10 different auto correlations and cross correlations, here's the measured and modeled change. So fairly good agreement. Here it is cross-plotted, measured and modeled change. And some details are mean free path and seismic velocity of 1.5 kilometers per second, mean free path of 2 kilometers. And also one other detail is because it was an increase, we did this positivity only. We only saw increases in these stations. So we, to get the best image, we said that the inversion needed to return a positive velocity change. Okay, and then the other remarkable thing is the dome is being extruded here at the vent, but the greatest change is here on the northwest side of the volcano. So that was surprising. For that, we looked at the geological map of Great Sitkin by Wei Thomas and others, and they noted that there's a collapse scarp. The northwest side of the volcano in the geological past collapsed into the Bering Sea, a catastrophic failure, an edifice failure of the volcano. So this whole sector of the volcano is different than this portion, according to this geological map. So the interpretation is that this is related to that the material properties of the northwest side of the volcano. So the material on the northwest side has higher susceptibility to the applied stress of that dome being extruded at the summit. And so it's closing the cracks more on the northwest side. It's almost like a side effect of Coda waves that you're seeing it more amplified there on the northwest flank of the volcano. Okay, and then just 2 more slides. This is for future work. We've also, following Ann's work, looked at decorrelation. And so this is looking at the correlation coefficient. It's in addition to time lag. Here also on August 1st, I've marked it with red. We start to see a decorrelation anomaly. So in Anne's work, there's also kernels for that, and we are planning to apply the inversion to see. My hypothesis would be that this decorrelation will also be on the northwest side of the volcano, but we will see. Okay, and then the last slide with data on it, just a summary of, comparison to earthquake variations. We see an increase in velocity instead of a decrease, and also we don't see weeks to months long healing of the velocity. It has increased and it has sort of plateaued, even to the current time. So it will be interesting to see if over the years if this does decrease, but for now, it is continuing, but it's slowly not increasing as much. There have been a few pulses of growth, but it's plateauing in the dome growth. So we'll continue to look at that in our monitoring. Okay, and then to wrap up, our final thoughts based on what we saw of infrasound arrays and this coda waves at Great Sitkin. Something at AVO that we want to do in the future, in the next 5 to 10 years, is because of the success of these infrasound arrays, we want to also now start to deploy real-time seismic arrays. So that's something low-hanging fruit. We have all the infrastructure to analyze arrays data in the observatory, so now we'll begin to put out seismic arrays. This is exciting news. What I showed here, this is, I think maybe Anne mentioned this, this is sort of ambient noise tomography in research mode, after, post-processing, I think is what Anne called it. But Tarsilo Hirona, he's at the university part of AVO in Fairbanks, and a visiting student, Laure Brenot from Brussels, they are just wrapping up a web-based real-time ambient noise display. And so this will come online soon, and that will become a more production type of monitoring for the observatory. And then last, if you're interested to go take a look, all our data are at IRIS in real time. Also, our earthquake locations are at Comcat. So you can, if you have time and interest, check it out. And with that, thank you.